Okay, morning folks. Going to do a quick revision session on balancing half equations for redox reactions. So again, in a redox reaction, there will be something that is losing electrons, i.e. being oxidized, and something that is gaining electrons, i.e. being reduced. And you need to show which species is doing what and also balance those half equations. I'm going to show you a few examples and use the O'Hay rule to balance the more complex ones. So we'll discuss the O'Hay rule first. All right, it's a very simple sort of list of instructions, if you like, for how to balance half equations at A-level chemistry. First thing is, all right, is the balance all atoms which are not oxygen and hydrogen. That is the first rule for anything. Okay, so in these two examples here, we're going to look at PB is balanced with PB, AL with AL, one of each, so there it's all balanced. Second rule is O's. All right, the O in O'Hay means you balance the oxygen atoms by adding water. So if you've got two oxygens on the left but none on the right, you would add two water molecules to the right-hand side. H is you balance the hydrogen atoms with H plus ions, hydrogen ions or protons, if you want to call them that. So again, if I've got four H's on the right but none on the left, I'd add 4H plus to this side. And the final one is the E minus, which is electrons. So you balance the charges with electrons, because the charge on either side, the total charge on either side, needs to be balanced. So let's work through these two here. So this is a nice simple one. Lead ions are 2 plus, become lead atoms. All right, so if you follow the O'Hay rule straight through, you'll notice that you balance the atoms. There are no oxygens. So we've done that bit. There's no oxygens or hydrogens. So now we just need to balance the charges. So on the left-hand side, the total charge is 2 plus. On the right-hand side, the total charge is 0. Okay? And here's the rule with electrons, and here's where students do make mistakes with this. Add electrons to the most positive side. Yeah, to make them balance, electrons are negatively charged. So you have to add them to the most positive side to make it balance. So you can see here, this is the most positive side because it's 2 plus. So how am I going to get from 2 plus down to 0? I need 2 electrons. Okay, so that's now balanced. Let's try the second one here. Aluminium. There are no oxygens and hydrogens, so we go straight to step 4 here. Balance the electrons. So on the left-hand side, there is no charge. On the right-hand side, it's 3 plus. Always add electrons to the most positive side. So I'm going to add electrons to this side, but how many to make it balance? Well, it's 0 on this side, it's 3 plus here, so I'm going to need a total of 3 electrons. Right? And you can also combine these half equations to make an overall equation. All right, and we'll discuss how to do that in a second. All right, but before we do, let's just focus on what's these equations are actually representing. This top one, the lead ions are gaining electrons, so I'm going to call that my rig. From oil rig, reduction is gaining of electrons. And here the aluminium atoms are becoming aluminium ions by losing electrons. So that is my oil. And that's quite important for being able to identify oxidizing agents and reducing agents. So we'll come on to that in a second. So I'm now going to combine the equations. So to make one overall equation. Now you'll notice in chemical equations, in overall equations, there are no electrons. So before you combine them, you need to make sure the electrons are balanced. And what I mean by that is, if something here is gaining 2 electrons, there must be something else losing 2 electrons. But you can see here it's not quite that straightforward, because the aluminium is losing 3 electrons and the lead ions are only picking up 2. So you have to make them balanced. All right, so obviously 2 doesn't go into 3 very easily, so you're going to have to find a common multiple. So I'm going to times the top equation by 3, and I'm going to times the bottom equation by 2, because that should hopefully give me 6 electrons. So if I times everything here by 3, so that becomes 6, that becomes 3, and that becomes 3. And the bottom one, I'm going to times everything by 2. Yeah. Once the electrons are balanced on either side in both equations, i.e. you've got 6 electrons, the number of electrons being gained and being lost are the same, you can then combine them. So everything on the left of the arrows, so everything on this side, becomes everything on the right side. So I'm going to include the electrons and I'll cancel that in a moment. So I'm just going to write everything on the left as I see it. 6 electrons plus 3 PB, 2 plus 2 AL. So that's everything on the left-hand side becomes everything on the right. And then you can start cancelling out. And like I say, electrons don't feature in overall equations, and because they are balanced, if you've got 6 electrons on the left and 6 electrons on the right, they can cancel out. So then it gives you the overall equation of 3 lead ions plus 2 aluminium atoms becomes 3 lead atoms and 2 aluminium ions, which is what you'd expect based on the work you've done on reactivity series at GCSE. Aluminium is more reactive than lead, so it will displace lead ions from one of its compounds. Now, what you might also get asked to do is identify your oxidizing agent and reducing agents. And it's just general rule over here, as in it's a fact. Oxidizing agents get reduced and reducing agents get oxidized. So let's just work on what does that actually mean. So oxidizing agents do the oxidizing. So if they're going to oxidize something, that something is losing electrons. So if that something is losing electrons, what's happening to me? I'm taking electrons away from something else, therefore I am getting reduced. And it's vice versa for reducing agents. So, oxidizing agents get reduced. Well, which of our equations was reduction? Well, it's this one here, the rig. So, the thing in the equation which is gaining the electrons is the lead ions. So the lead ions are my oxidizing agent. Okay, and that must mean that the other thing, which is the aluminium, must be the reducing agent. Okay, and just check, because if reducing agents get oxidized, are my aluminium atoms getting oxidized, i.e. are they losing electrons? Yes, they are. Just be cautious with this one here. The oxidizing agent, it is the lead ions technically, but you can't just go to a chemistry stockist and say, give me a bucket of lead ions. There will be a spectator ion which is not in the equation, so it could be sulfate, for example, or chloride or something like that. So be careful, don't just put the ion. The oxidizing agent is a chemical reagent. It's something you can buy in a bottle. So it could be, you have to read the question, it could be lead chloride, it could be lead sulfate, it could be lead nitrate. So just be careful with that. Okay, right, I'm going to just pause the video now, I'm going to clear the board, and then we'll try another example. Okay guys, got another example here. Got lead dioxide becoming lead ions and chloride ions becoming chlorine. And I'm going to first apply the O'Hay rule to both. Okay, so let's apply the first one then. So balance the atoms which are not O's or H's. So I've got 1 PB there. So that's the first one done. Now balance the O's with water. So you see I've got 2 oxygen atoms on the left. I've got no oxygens on the right. So I need 2 water molecules, because each water molecule contains 1 oxygen, and because I needed 2 oxygens, I need 2 lots of water. So that's the second rule. Third rule, the hydrogens. So I've got no H's on the left hand side, but I've got 4 on the right hand side. So I'm going to add 4 H pluses there. Okay. And the final stage is the charges. So again, add up all the charges on both sides. So on the left-hand side, I've got a total of 4 positive species. So that's plus 4 in total. All right. Or let's call it 4 plus for continuity. And on the left-hand side, I've only got 2 plus. Yeah. So it's 4 plus on the left. Sorry, 4 plus on the left, 2 plus on the right. Add electrons to the most positive. All right, so the overall charge on either side, add electrons to the most positive. So hopefully you can see 4 is bigger than 2. So I'm going to add electrons to this side. How do I get from 4 down to 2? I'm going to need 2 electrons. Yeah. And the next stage is the chloride one. This is quite easy because there's no O's or H's going to be in it. So it's just a simple case of balancing it and adding the correct number of electrons. So 2 chloride becomes Cl2. Now the overall charge on this side is 2 minus, and on this side there is no charge. So again, I'm going to add electrons to the most positive side. Well, that's a negative number, that's 0, so that is technically the most positive side. So how many electrons will I need? 2. All right, and then that will make that into minus 2. So then, I'm going to do the oil rig part now, just for when I have to identify the oxidizing agent, reducing agent. So electrons are being gained up here, which because they're on the left-hand side. So this process here is rig. So there's my rig. My reduction is gain of electrons. And here the electrons are on the right-hand side. So that is very much my oil. Okay. So that will help me. Okay. So I know that oxidizing agents get reduced, which means my oxidizing agent must be in this equation. And I know my reducing agent gets oxidized, so that must be in that equation there. And we can combine them now, all right? And I'll do a quick shortcut here because I know everything on the left will become everything on the right. I've got 2 electrons on the left, I've got 2 electrons on the right, so I'm going to cancel them out and then just write everything I've got. 4H plus PbO2 plus 2Cl minus. That is everything on the left-hand side of this particular of these 2 half equations, and that becomes Pb2 plus 2H2O plus Cl2. All right, and that is a balanced overall equation. Yes, there'll be some spectator ions potentially in there, but obviously we don't need to show those because they're not taking part in the chemistry. So the oxidizing agent, reducing agent, going back here, the oxidizing agent gets reduced. So what was the species in this equation? All right, well, we added the H plus, so we can ignore that. All right, it's that one there. So there is my oxidizing agent, OA. And then the next one is my reducing agent. So reducing agents get oxidized. So it must be in this equation here. Yeah. And because your oxidizing agents and your reducing agents are reactants, they must be at the start of a chemical equation. You know that they're going to be on the left-hand side somewhere. All right, so they're quite easy to spot once you know what is the oil and what is the rig half equations. Okay, so if you pause the video, we'll do another couple of examples in a moment. Okay, guys, we're going to look at the reaction between sulfuric acid and iodide ions right now. Very much you need to know these equations. Well, not know them, but be able to work them out and also report on the observations, as you've discussed in the halogens topic. So again, I'm going to do the O'Hay rule exactly the same as before. So balance all the atoms which are not O's and H's. So S, I've got 1S there, 1S there. Jobs are good, and that one's sorted. Balance the O's with waters. So you can see I've got 4 O's on the left, none on the right. So I'm going to need 4 H2O's. Now, balance the hydrogen atoms with H pluses. So just be cautious here. You can see in total I've got 8 hydrogens there, 2 there. So I've got 10 hydrogens on the right hand side. On the left, I've got 2. So that means I need another 8 hydrogens on this side. Okay? And then I need to balance the the electrons. So balance the charges with electrons. So in total, on the left hand side, I've got 8 positive hydrogen ions, so that's 8 plus. And on the right hand side, I've got 0 charge. So again, you need to add electrons to the most positive side in terms of overall charge. So here, I've got 8 plus on the left, nothing on the right, so I'm going to add 8 electrons there. Okay, and the next one, there's no O's and H's, so it's quite straightforward, this one. 2 iodines, only 1 iodide, so I need to double that. And then again, add electrons to the most positive side. So here, I've got 2 minus on the left, and on the right, I've got 0. So I'm going to add electrons to the right-hand side this time. You can always check as well, all right, because if this is a redox reaction, one of your half equations will be reduction, i.e. the electrons will be on the left, and one will be oxidation, the electrons will be on the right. If after you've done this process, you end up with the electrons on the same side for both half equations, you've made a mistake, so you might want to start again. So everything's now in place, all right, but again, before we combine these, let's just make sure we're aware of what's oxidation, what's reduction. Electrons on the left-hand side, that is very much reduction. So that's my rig. All right, so already I know that because it's the reduction half equation, my oxidizing agent is in there somewhere, so that must be my oxidizing agent, sulfuric acid. All right, we'll write all that at the end. And this is my oil. Oxidation is loss of electrons. The electrons are on the right-hand side, so the iodide ions are getting oxidized, which means they must be the reducing agent, right? But before we combine them, we need to make sure the electrons are balanced. 8 electrons being gained, only 2 electrons being lost. So I'm going to have to times everything in the bottom equation by 4. So that becomes 8I minus 4I2, 8 electrons. And then once the electrons are balanced, you can combine them. So 8 electrons being lost, 8 electrons being gained. Everything on the left becomes everything on the right. So get my arrow in place. 8H plus. Okay. And there we go, that's it, simple. And like I say, the observations you get with this particular one, hydrogen sulfide, you get the rotten egg smell, all right, and iodine being produced, you'd end up with a black solid which may dissolve in some of the water to make a brown solution. And you get other observations as well using different half equations. And this proves that iodide is such a powerful reducing agent. It can reduce sulfur all the way. Well, I'm going to assign oxidation state here. The oxidation state of sulfur there is +6. And there it's -2. So the sulfur atom is being reduced by +6 down to -2. Well, how will it do that? It's being reduced. Reduction is gain. Well, how many electrons does it need to gain to get from there down to there, which is the difference, which is 8 electrons. If you go back to the half equation, it's shown you that. Okay, so the oxidizing agent is the thing getting reduced. So what is being reduced? It's the sulfur atom, but you wouldn't say that sulfur is the oxidizing agent because there's no such thing as elemental sulfur on its own in here. So it's the oxidizing agent is the chemical which contains the atom or atoms which are being reduced. So that is my oxidizing agent. And therefore this, which is in the other half equation, must be my reducing agent. Okay? I'm going to show one more example, so if you'd like to pause the video now, and then I'll just clear the board. Okay, folks, last one. Just going to apply the O'Hay rule again to these two half equations, then combine them, and show you that these are a very specific, special type of redox reaction. So, top one, balance the Cls first. They're already balanced. Second one, balance the oxygens with waters. So you can see I've got 3 oxygens on the right, only 1 on the left. So that means I need 2 waters on the left. Next stage, balance the hydrogen atoms with H+. So I've got 4 hydrogens on the left, none on the right. Jobs are good. Now let's balance the charges. So got to be careful here. So in total, on the left-hand side, I've got 1 single minus ion, so that's 1 minus. On the right, I've got a 1 minus there, and I've got a 4 plus there. So in total, if you add those together, that equals 3 plus. Okay, and I'm going to add electrons for the final step of the O'Hay rule. Always add electrons to the most positive side in terms of overall charge. So here, I've got to get from 3 plus down to -1. So in total, I'm going to need 4 electrons. So 3 minus 4 does equal -1. So that's sorted. And this next one, Cls are balanced. I'm going to add a water to this side to balance the oxygens. 4 H pluses to this side. And then when I try and balance the electrons now, on the left-hand side it's 3 minus, and on the right-hand side it's 1 minus. So it's sorry. On the left-hand side, it's 3 plus. On the right-hand side, it's 1 minus. It's the reverse of the top equation. So I know that I'm going to have to add 4 electrons to this side. Okay. Now, good news is that the electrons already balance. So the electrons being gained, all right, so this is my reduction, equal the electrons being lost. So 4 electrons being lost at the top, 4 electrons being gained at the bottom. So there's my oil. And you'll notice there's something else. There's a few other things we can cancel out here. All right, so you can see that 4 H pluses are being lost at the top, and 4 H pluses are being gained there, so they cancel out as well. And is there anything else that cancels out? Well, there's 2 waters on the left at the top, and there's 2 waters on the right at the bottom, so they cancel out. Again, if you want to prove this, you could literally do what I did earlier in the video and just write everything on the left becoming everything on the right, and then just cross the F things that are common on both sides. And now, when you combine these, you end up with ClO minus plus ClO minus. So what I'll do there is, I'll just get rid of one of those and just put 2. Becomes ClO 3 minus and Cl minus, okay? And this is a very specific type of redox reaction, because you can see there's only really one chemical species on the left-hand side. Well, oxidation is loss, and my reducing agent gets oxidized. So I know that that must be my reducing agent. So that is my reducing agent. But if it's the only chemical on the left-hand side, it must also be the oxidizing agent by definition. So that lets me know that one of these ions is the reducing agent and the other one is the oxidizing agent. And there's a very specific name to this type of redox reaction. It's called a disproportionation. It's a disproportionation reaction where the same chemical species is being simultaneously oxidized and reduced. Or in other words, where your reducing agent equals your oxidizing agent. It's a very specific form of redox reaction. Okay. So again, that's just a little walk through balancing half equations and the O'Hay rule. All right, and there's plenty of examples out there for you to try. Okay, hope this helped.